Hello everyone. My name is Greg Chadwick. I'm the digital design lead at lowRISC. That is the same organisation that Gavin works for. He is the CEO. I'm here to tell you today a bit about open source and specifically about open silicon and why this is relevant to the CHERI ecosystem. So first of all, let's just have a talk about what I mean by open source and open silicon. So hopefully everyone in this room understands what I mean when I talk about open source software. And it's very widely deployed, and it's really a foundational part of modern computing. Typical example I always use is the Linux operating system. It is everywhere. Most people build things on top of it. But what about kind of open silicon? So when I'm talking about open silicon, I'm talking about the idea that the design of your chip is open in the same way that open software would be open. So the code, so in this case the RTL, something like the system Verilog, is actually available under a permissive license, like an Apache 2.0 license or any of the other open source licenses you might care to use. And unlike open software, we really don't see much open silicon like in the wild actually being used. It is out there. You might be surprised to find the places it's ended up. But it's often kind of hidden around the back and no one really talks about it. And that's one of the things that lowRISC is really trying to change. And it is something we're already doing with OpenTitan. And of course, Gavin went into quite a bit of detail about all the collaborative engineering and Silicon Commons working practices. And I think it's important to point out that CHERI development has already benefited quite a bit from open silicon. So looking at kind of prototype CPUs, things coming out of the Cambridge Computer Lab, we've already been seeing those released as open silicon, as kind of research prototypes. So the early MIPS CPUs and the more recent kind of RISC-V prototypes, you can go download those. If you go on the Computer Lab, you can get hold of them. And this makes makes it easier for people to get their hands on this technology and try it out. And then we also have the Microsoft's CHERI Ibex core. So in the one of the earlier talks, we're going through kind of CHERI, talked a little bit about CHERIot as well. And I'll go into a bit more detail then. And this is a really interesting core, and it's moving towards production. It's going to be moving towards actual silicon that people can buy, which is really exciting. So one question to ask here is, open source has been a massive success, so what challenges are standing in the way of open silicon to maybe make it a similar success? Well, there are some similarities of open software, but it's also got some unique challenges as well. I think one thing, major challenge of open silicon is DV, design verification. Obviously, software also requires testing. But software doesn't have to be taped out into a physical artifact. So generally, the kind of verification standards needed out of a production silicon design are significantly higher than people might be pushing in standard software, at least. If you're talking about, say, safety critical and these kinds of software, then it looks a bit different. But for standard software, the standards here are often a lot lower. And the verification of your open silicon needs to be kind of complete. You need to be able to present full coverage to demonstrate you've actually tested all possible areas of the design. And no one really wants to commit to using your design if they don't have high confidence it will work. As saying, the standards to achieve are generally very, very high for a commercial tape-out. And the reason for this is, and I guess for the people who aren't aware when I talk about tape-out is the process by which you finish the design and you send it to a silicon foundry to be made. So it's kind of the point of no return. You're saying, here's my design, please build it. Tape-outs can cost millions of dollars. That's literally to just get it to the foundry and to get them to start making it. That isn't involving the cost of actually getting to the tape-out in the first place. And so they're very expensive. They also have very long lead times. It can take many months to get a chip back get manufactured off the end of a tape out, and then you've got to test it and verify it. So if you mess it up, it's a very, very expensive, potentially millions of dollars mistake. And this is why your standards are very high for tape outs and DV. And then another issue here is the tooling required to build open silicon, to build any silicon design is expensive and also proprietary. And again, that's a bit of a difference from software, where good compilers nowadays are open source, widely available, and generally state of the art, best in class. They're the things you use. So it's interesting to maybe drill down a bit into comparing things against the software world, because obviously massive success in the software world with open working practices. So what can we take from the software world? And there's plenty of good things we can draw from there, but we've got to realize there's also some differences. and table here that kind of goes into a few of them. Again, other issues, there's maybe far fewer skilled engineers around in silicon design than there are in software. And again, you have this big problem that it's just so much more expensive to get a working silicon product out there to use versus a piece of software where it's maybe a lot cheaper to at least trial using it, give it a go, and then you can maybe kind of back out and go somewhere else if you're feeling, if you need to. Silicon, you end up having to commit, and the costs of committing, if that goes wrong, are far higher. So how do we fix this? Can we produce good open silicon? And I think the answer, lowRISC, is yes, absolutely. OpenTitan, which Gavin went into earlier, is a really great example of a bunch of open silicon working practices and how we can actually get to good open silicon that can tape out into commercial designs. I'm just going to zoom in into one part of the OpenTitan project, which is the IBEX RISC-V core. So this is an open source core. It's for embedded kind of low end use cases. It's got a variety of features, including a bunch of security features because it comes from OpenTitan, a security chip. But crucially, it also includes kind of full production quality DV, which is also fully open source. So people can actually verify for themselves that our design is sound by looking at all of our test suites and rerunning them. And in building IBEX, we've managed to demonstrate how to build a kind of production quality CPU core that is going into real products. It's going into a Chromebook security chip, for instance, as part of OpenTitan, and many others are deploying it elsewhere. And it really demonstrates a way that you can produce good open silicon that can be used in real shipping designs. So now it's interesting to maybe talk about Chariot IBEX. So I'm not going to go into all the details about Chariot, but fundamentally, Chariot is a cut-down form of CHERI, or maybe a form of CHERI that's been targeted at lower-end use cases. So it's designed for kind of embedded hardware, things like operational technology, IoT, etc., etc. And it's actually a lot of these cases that I think the earlier digital security by design cohorts were finding that people were interested in using, and they're spending all their time trying to work out how to make the Morello board interface with these kind of little peripherals they have. And they maybe wanted something lower end to start with. And this is something that Microsoft has created. But it's interesting just to take a step back and understand where Chariot IBEX, specifically, so the CPU core implementation of Chariot has come from. So, back in ancient history at this point, ETH Zurich created this open silicon RISC-V CPU called lowRISC as part of something called the Pulp project. And they contributed that back to lowRISC, where we renamed it IBEX, intending to use it in OpenTitan. And working with the OpenTitan partners, we really expanded that core, added a bunch of features, and critically built all this production-grade DV. We took what was a nice little core that had been taped out and had been used in a variety of effectively research chips that the Pulp project had done, and we kind of took it to the next stage, and we turned it into production-quality IP that you can use in a kind of real design and have confidence to be shipping out hundreds of millions of units that are relying on this CPU working correctly. Meanwhile, whilst we're off doing this, Microsoft are realizing that maybe it would be interesting to have a version of CHERI that's designed for these kind of lower-end embedded cores. And so they begin this project to start scaling down all these ideas in CHERI to embedded cores, and they produce Chariot, this ISA, which is fundamentally a RISC-V extension. And then they're looking around to determine, well, we need to be able to actually test this out. We need to build an implementation of it. And they pick up IBEX, because IBEX is already this kind of production quality CPU core that they can then add Chariot on top of and give themselves a very solid base for their first implementation. That is announced. We have some engagements with Microsoft. We also have some engagements with the UK government through UKRI. And that produces the Sunburst project. And this is what produced the Sonata board that Gavin was showing off earlier. And this exists to produce an evaluation platform for Chariot. So this allows you, before the real silicon exists, the Sonata board gives you the Chariot design on an FPGA in a form factor that kind of embedded system engineers can use, where they can just write some code, load it onto the board, interface it with devices, and they can get on and use it, and they can trial using kind of Chariot or more broadly CHERI technologies in their use cases. And then we also have SCI, who are also here today, who have announced Iceni, and yesterday we announced that we are working with SCI to integrate some of the open technology we've been working into CHERI. And this is going to give us the first kind of commercial CHERI implementation based on CHERI IBEX, and indeed will hopefully be one of the first kind of fully available CHERI implementations out in the market. Oh. So, we've taken IBEX. I'll say we've taken IBEX. Microsoft took IBEX, and it has become CHERI IBEX. So they've shuffled things around and added a few extra things in order to give you all this CHERI functionality. And we've had an engagement with Microsoft to start investigating how to do the DV, the design verification of the design. Because, as I said, it is vital to have good DV to actually get to a production quality design. Got a nice quote there from Tony Chen, who's one of the security architects at Microsoft about this work. So as I was saying, one of the hard parts of building open silicon, or rather in order to get open silicon into production devices, is how you do the design verification. And for CHERI IBEX, that's going to be no exception. And at the moment, it isn't fully verified, although it is a very high quality core. There's an awful lot of testing that's already got into it, so we've already got very high confidence in it. But we don't quite have the coverage levels that you might have for a full production tape out. So there's a bit of a question of, well, where do we go next? Well, again, kind of open silicon's really going to help us here, or more broadly, open source working practices. So we're starting from a very solid foundation. The base IBEX core is already verified to kind of production quality level. And there's an existing framework we use to verify this called RISC-V DV. This generates random RISC-V programs for you, which you then run on your core and check they work correctly by comparing them against a simulator. So we'll be looking to extend RISC-V DV so it can generate chariot code, and then use the SAIL model, which is the kind of reference model for the chariot architecture, as well as for RISC-V as a whole, and it will be able to check the correct function of chariot programs against the SAIL model. There's also a new methodology that we're looking to use called TestRig, which again comes out of Cambridge Computer Lab. They designed TestRig to help them test some of their CHERI processors. And again, we'll be looking to use this to help verify CHERI IBEX. TestRig is really great at getting into some of really detailed corner cases that you might find in a capability-based architecture. So it's really useful for testing complex CHERI-specific behavior, which is why Cambridge Computer Lab built it. Also, very excitingly, we've been doing, again, collaborating with people, we've been working with others on an end-to-end formal solution. And this will actually prove equivalence of the CHERI IBEX core against the SAIL model. And this is like a really strong result. You're saying mathematically this CPU core behaves exactly as the model says it should behave. And this work's actually come out of Oxford University. And yeah, I'll talk a little bit more on the next slide. And each of these methods has its strengths and weaknesses. I've got this little Venn diagram here just to indicate that each of these things will end up testing the same thing in the same way, but that's often a good thing to do for a CPU design because you really want to get very high confidence in your testing methods. And ultimately, all of your testing methods are going to have blind spots, they're going to have issues, they're going to have bugs. If you test the same thing multiple different ways, it's far more likely you're going to shake out all of the possible bugs. And it's thanks to open source that we can actually easily leverage all of these methodologies. Because all of these things have actually been developed in the open, it's easy for us to bring them together and to use them on CHERI IBEX. So we can end up with a higher quality overall design. Just a bit more about the end-to-end formal. So this work came out of Oxford, a group led by Professor Tom Mellom. And it produces what's called an unbounded equivalence against the chariot SAIL model. And this is, I won't get into all the technical details, but this is a very, very strong result. It is kind of proving mathematically that the CPU is correct. It does have a few caveats, unfortunately, so there's a few blind spots. There will be some more details about that when it's all released. And actually, so one of the students who did a lot of the work on this, Louis Emile, was an intern at lowRISC this summer, and he's been working on expanding the work he did under Tom, and that has included formally verifying our vanilla RISC-V core along with the CHERI IBEX core. We're going to be releasing it very soon under an Apache 2.0 license, and Tom Mellom's group's going to be publishing a paper on arXiv that goes into all of the gory details. And I think a really key point here is this is, I think, really interesting piece of work, really pushing the quality bar on the IBEX core and the CHERI IBEX core. And none of this work would have happened unless we had open silicon. Because the Oxford group, they wanted to do this end-to-end formal work. They obviously needed a CPU to verify. They were able to pick up the CHERI IBEX core as like a fully complete, close to production quality CPU to actually do the work on. Without open silicon, they wouldn't have had access to that. And then Oxford are then willing to contribute things back to the commons. And again, we can pick that up, we can work with Oxford, and then we can use it to help verify CHERI IBEX as well as vanilla IBEX for kind of full production design. So it's an example of a really great virtuous cycle, the kind of things that you get when you indulge in open silicon. And this is the kind of open working model that you see in open software in general. And again, just to emphasize, the kind of key role of open silicon here in the creation of CHERI. So we had a production-grade IBEX core, and that gave Microsoft a solid base to build from. And that meant that they could concentrate on building Chariot. They could concentrate on all the things that make Chariot, rather than just having to build a RISC-V core. They already had a nice solid base to start from. And Microsoft's decision to then release all this work back into the open under the Apache 2.0 licensing means that then this work can be transferred elsewhere. Everyone can look at Chariot IBEX and use it. So that's created this Sonata board for us, which has allowed evaluation and use of Chariot in advance of production silicon. So, those boards are available now. We've distributed over 100 of them via the UKI grant. They're available to buy on Mauser. As Gavin was saying, we've just released our 1.0 version of those boards, which is the kind of first fully stable version of the system, and it gives you an awful lot of features for people to play with. So the new Digital Security by Design cohort are all building on the Sonata system. Other interesting thing here is all of the work we've been doing in OpenTitan to build that IP. That IP is being reused in various places. So Revos, a big RISC-V startup, very well funded, recently announced, I think, a $250 million round. They're integrating OpenTitan into their SoC. You see Calyptra, which is another open silicon project, again, around kind of root of trust and security. They're also leveraging the OpenTitan IP. And then we have a really nice example from SCI as a small startup. They're successfully, we certainly hope they're going to successfully produce a nice commercial piece of silicon, which is going to be a microcontroller. And they're going to have done this with, fairly limited resources because of open silicon, because the core's already there, and they're also leveraging various peripheral IP, things like I2C, SPI, USB from OpenTitan. So again, SCI can get on and build the bit that's interesting for their business case, for their commercial work, without having to rebuild all this foundation, and they can really kind of leap forward without needing, without needing to build all this extra stuff out once again. And then, final slide here, just talking about moving beyond CHERI prototypes. So Sonata obviously is a prototype. It's not real silicon. There's certain limited production use cases you might want to use in FPGA, but mostly people are looking for the real chips. But it's really important to point out that open silicon, I think, has really played a vital role in helping enable some of this CHERI research and development, helping create FPGA-based evaluation platforms that have been widely used. And I think open silicon can continue to play a vital role in building production CHERI silicon. Because if you've got high quality, fully verified design, it provides a solid foundation to build commercial designs on top of. It allows you to create more available silicon to provide a healthy ecosystem, so others then have confidence building on it, because see more designs in the ecosystem, more happy to build things on top of it. And I think history's also shown that second sourcing is incredibly important. You don't want a fledgling ecosystem to get brought down because there's been a single commercial failure. By having all of this foundation in the open, if a particular commercial venture doesn't pan out, then well, it's a lot easier for others to come in and also do, try their own designs. And then, on top of all of this open work, there's plenty of room that will allow kind of commercial innovation and differentiation on top of an open silicon base, which is really vital because ultimately you need to sell this for money, you need to make profits, and that can then reinvest back into the ecosystem. And there's definitely plenty of room to do that on top of open silicon design. And yes, I think that's it.
Fantastic.
Thank you.
Thank you, Greg.